Section 14.1, Basic Concepts of Graph Theory. A graph is a collection of vertices, at least one, and edges. Each edge goes from a vertex to a vertex. This is not a graph like an x-axis and a y-axis. Not that kind of graph. Example 1. Miss Katz has 10 children in her preschool class. She observed their play patterns over a 2-week period and compiled the following data. She listed each child's name and who they played with. It's not easy to see the friendship patterns in the table, but the patterns are easy to see if we draw a graph. Each vertex represents one of the 10 children, and an edge connecting two vertices indicates their friendship. Draw the graph here. So we're going to say A for Andy, C for Claire, D for Dave, E for Aaron, G for Glenn, J for Joe, K for Katie, M for Mike, S for Sam, and T for Tim. Go ahead and put a point, and those are our vertices. Each child gets a vertex at their name, at their initial. Okay, Andy played with no one, so we don't draw any lines from Andy. Claire played with Dave, Aaron, Glenn, Katie, and Sam. Dave played with Claire. We already have that line. He also played with Aaron. Dave played with Glenn. And Dave played with Katie. Dave played with Claire. Dave played with Aaron, Glenn, and Katie. Aaron played with Claire. We already have that line. Aaron played with Dave, and Aaron played with Katie. Draw another line towards Katie. Glenn played with Claire, Dave, and Sam. So from G to S is another line. Joe played with Mike and Tim. Katie played with Claire, Dave, and Aaron. We already have those edges drawn. Mike played with Joe. We have that line drawn. Sam played with Claire and Glenn. And Tim played with Joe. That is the graph. A simple graph has only one edge between any two vertices. No edge goes from a vertex to the same vertex. A graph is connected if one can move from each vertex of the graph to every other vertex of the graph along edges of the graph. The connected pieces of a graph are called its components. Example 2, how many connected components are there in the graph below? We can start by tracing it, and here is one component. If we start at this point, this vertex, there is a second component. Starting at this vertex, here is a third component. Can be shown in 3 different colors. So there are 3 connected components in the graph. Two graphs are isomorphic if there is a one-to-one match between vertices of the two graphs, or whenever there is an edge between vertices in one graph, there's an edge between the corresponding vertices in the other graph. Example 3 asks, are the graphs A and B isomorphic? We can go ahead and label the vertices. graph A has a edge from A to B and from A to B, from D to C and D to C, B to C, B to C, B to D, B to D, A to C, and A to C. There is an edge between each of the corresponding vertices. Graphs A and B are isomorphic. Example 4. Are graphs C and D isomorphic? No, C and D are not isomorphic. There are 8 vertices in graph C and 9 vertices in graph D. There is not a one-to-one match between the vertices of the graph. The degree of a vertex is the number of edges joined to a vertex. Example 5 says find the degree of each vertex in example 1. Degree A is just the vertex. There are no edges. Its degree is 0. From C, we can trace it. There are 1, 2, 3, 4, 5 edges going out from C. The degree is 5. Count them from D. 1, 2, 3, 4. E. 1, 2, 3. G. 1, 2, 3. J is 2. K is 1, 2, 3. M is 1. S is 2. And T is 1. The sum of the degrees, add up those degrees, 0 plus 5 plus 4 plus 3 plus 3 plus 2 plus 3 plus 1 plus 2 plus 1 is 24. The number of edges is 12. The sum of degrees theorem says that in any graph, the sum of the degrees of the vertices equals twice the number of edges. Example 6. A graph has 6 vertices, each of degree 3. Determine the number n of edges this graph has. Then draw a graph with 6 vertices and n edges. There are 6 vertices, each of degree 3. 6 times 3 is 18. 18 divided by 2 is 9. So there are 9 edges. Draw a graph with 6 vertices. 1, 2, 3, 4, 5, 6. And 9 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, what am I missing? 16, 17. I believe there are 18. Example 7. The table below indicates bus connections between several cities. Draw a graph with vertices representing the cities and edges representing a direct bus link between 2 cities. Okay, we'll use G for Grand Forks, F for Fargo, B for Bemidji, C for St. Cloud, D for Duluth, M for Minneapolis, E for Escanaba, and I'm going to use GB for Green Bay. Grand Forks goes to Bemidji and to Fargo. Fargo to Grand Forks, Fargo to St. Cloud, Fargo to Minneapolis, Bemidji to Grand Forks, and St. Cloud. St. Cloud to Bemidji, Fargo, and Minneapolis. Duluth to Escanaba and Minneapolis. Minneapolis to Fargo is already there. St. Cloud, Duluth, and Green Bay. Escanaba to Duluth and Green Bay. And Green Bay to Escanaba and Minneapolis. The table below indicates the bus connections, similar to what we just drew. This is just a different representation of the same thing. If you put your letters in a different order or in a different place, your graph is going to look different. We need to list 3 different routes from Minneapolis to Grand Forks. So we can go Minneapolis, Fargo, Grand Forks. We can go Minneapolis, St. Cloud, Fargo, Grand Forks. We can go Minneapolis, St. Cloud, Bemidji, and Grand Forks. If you wanted to take the long route, you could go Minneapolis, Green Bay, Escanaba, Duluth, back to Minneapolis, St. Cloud, Fargo, Grand Forks. These routes are examples of walks. A walk in a graph is a sequence of vertices, each linked to the next vertex by a specific edge of the graph. Think of a walk as a route you can trace without lifting your pencil. A path in a graph is a walk that uses no edge more than once. A path may use the same vertex more than once. Here's our graph from example 7. Decide which of the following sequences are paths. Minneapolis, St. Cloud, Fargo, Minneapolis, and Duluth. Is it a path? We traced it without lifting our pencil, so yes, it's a path. Bemidji to St. Cloud to Fargo, Fargo to Minneapolis, Minneapolis to S1? St. Cloud, and St. Cloud back to Bemidji. Yes. Did we lift our pencil? No, we did not lift our pencil, so yes, it's a path. Minneapolis to Duluth to St. Cloud. No, not a path. We do not have a direct line from Duluth to St. Cloud. A circuit in a graph is a path that begins and ends at the same vertex. Begins and ends at the same vertex. Find 3 different circuits you drew in example 7. Still using our same cities, we're going to say Bemidji, St. Cloud, Fargo, Grand Forks is one circuit. Fargo, St. Cloud, Minneapolis, and around again. Minneapolis, Green Bay, Escanaba, and Duluth, all the way around. Those are circuits. Example 10 says refer to the graph below. Classify